Okay, I think we're all ready to go here. So yeah, now yesterday you guys kind of started your SDS stuff too. Yeah. Okay. Hopefully that's fairly straightforward. But now, okay, 5.6 here. What we're going to do is we're going to wrap up by combining both electric fields and currents with magnetic fields and magnetic forces. Okay, and it gets into electromagnetism. All right, so it's a neat little application when you combine both of these. So, current and fields. When we talk about electric current, that's actually the electrons moving through some kind of conductor, typically a wire. Okay. If you move a magnet close to a wire, you can actually create your own current. The magnetic force will actually help move the electrons. Okay. If you move charged particles close to a magnet, you can deflect the magnet. So these two forces will interact with each other. Okay, the electric field and the magnetic field work kind of opposite of each other and interfere with one another.
Is that how they get right?
Yes. Well, partially, yeah. But it can lead to things like more powerful magnets or electric field being producing electricity. That's how we produce electricity. Is you spin turbines, right? And those turbines are magnets. They're wrapped around a copper wire. By doing that, you create this electric field, and then you can charge your smartphone, drive your. Exactly, yeah. All those things. Okay? So, this is how they're connected. All right? Now, magnetism, there we go. Tough word to say. Together, the interaction between electric and magnetic field is known as electromagnetism. Holy cow, I'm having a tough time with that word today. Basically speaking, moving magnets generates current in stationary wires. All right, and moving charges generates electric fields. So that's how they're related. No, moving charges generates magnetic fields. Okay, so they kind of work off of one another. One kind of creates the other. So there's this cool, neat little relationship there. If you actually ever watched Cosmos, they have some cool stuff on like Faraday and Tesla in there, how they did their work. Because they knew that they could find this relationship, but they didn't know what it meant yet. So it's really neat to kind of watch all that. What's that? They weren't Einstein. It was 200 years before Einstein. So, you know, you're working with electricity.
Tesla was.
Not Tesla, but Faraday was. Yeah, and you're working with this stuff. And like, you know there's something there, but you don't know what yet. You're limited on what you have for technology and knowledge and everything. So it's kind of neat to see how they came up with some of that stuff. Now, the actual relationship between these two was originally discovered by a Dutch scientist named Hans Christian Oerstede in the early 1800s. He was actually able to tie it all together. Okay. All right, inducing currents. Now, when you move a magnet field close to a wire, you induce a current in it. Okay, so you're actually going to force a current through the wire. The area of creating currents in wires by moving magnets is known as electromagnetic induction. So what this means is you're creating an electric current by moving a magnet. When you do that, electromagnetic induction, okay? So what that looks like is when you do electromagnetic induction, is you actually change the reversal of the current. Typically, with an electric current, your electrons here, I can't draw on anything. So what happens is your electrons, So your electrons here, they move from the negative pole up to the positive pole. That's how the battery works. That's how electricity moves. Okay? When you move a magnet close to it, so let's say your magnet's here, what you actually do is you basically reverse it. And you make the electrons go from positive here up to the negative pole. Okay? So this one here is induction. Now, we can actually find the direction based on the old right-hand rule. I actually did some research, and you can actually find the left-hand rule and use instead. But I thought we'd just stick to the old right-hand rule. Why start throwing in two hands? Okay? Exactly. You could use both hands and then forget which hand's for what, and then you're in the middle of a test just looking at your hands and not knowing what to do.
You're going to look back at us with that drink time. We're just going to be like holding our in the air, holding a test out like this.
I'll have to try not to laugh during the test then. That'll be tough. So what the right-hand rule does is, like, this is your wire here, okay? What you do is you take your right hand and you wrap it around the wire in the direction of the magnetic field. Okay, so the magnetic field here is turning this way, around and around and around the wire. What you do is you take your right hand, you go like that, in the same direction as the magnet, and whatever direction your thumb is pointing, so my thumb is pointing up,
The direction.
that's the current, okay?
What if you go like this?
Don't do that.
What if you're like this instead of that?
What's that?
If you're like that, that thickness thing.
Then you're not going in the direction of the current.
Okay, so your current's on this way, right? Yes. So you're up like this. Technically speaking, you're still right.
Mm-hmm. Now this is where it gets a little funny. So this is the direction of the current based on the magnetic field, but through induction, what happens to that current? It goes in reverse, right? See, normally it goes up to the positive, or up to the negative, sorry. Oh, wait, no, that's wrong. Sorry. This is right. Oh, no. I got no choice. We got to adapt. So no, that was wrong. Sorry. If you look, current usually travels from negative to positive, right? But with the induction, it's going to go in the opposite towards the negative. So this is right. Sorry. You turn off that magnet, though, which way would the current actually flow? Right. It should actually flow that way. Okay?
So the magnetic field is generated by, which means that it's generating the on the thing that's taking.
Well, yeah. The only reason there's a current there in the first place is because of the magnet. So if you turn off the magnet,
Tidal, so the magnetic field is generated by.
Yeah.
Yeah.
Sorry. Yes, that's right. The magnetic field is being created by the current. But there is a magnet in there, but you run electricity through it to create it. Okay. Yeah. Yeah. That was what we talked about at the beginning. Remember?
No.
We said moving charges generates magnetic fields.
At the beginning of this lesson.
Yeah. Yeah. Let's do that. Just work on that computer there. It should work for you.
Can I go find it?
Yeah, absolutely. Do you need help with something?
I have to write a few questions like for the text.
Oh, okay, yeah. Go track her down then, Sam. That's important. Adam, do you need to go? You good? Okay. Keep you posted. All right. Oh, yeah. Here you got the flow. Here's your current. Right, something like that. Thank you. This is the P-value. Now, if you were to draw vectors coming off of here at 90 degrees, I know this isn't very neat, guys, but work with me. It's actually your work. Vectors in three-dimensional space around non-visible curve. What's that? That's showing the work. Because it's actually doing movement. Yeah. Okay. So that's how that works. Just think, guys, it could be worse. You could be the ones having to watch this video at home.
That's true.
Right? Who's getting the last lap now?
I think the way David's
That's fine.
No, it'll help.
It'll help them. Now they're laughing. Now it's not so daunting. I used humor to diffuse the situation.
See, it's fine. It's probably not one.
This is the formula calendar.
This is the one I gave you guys on Tuesday, yes. Okay?
You give us the.
What's that?
You give us the.
Well, I gave you the wrong side. But you can still use this.
40 minutes.
Oh, whatever.
It's fine.
It's a cold day, guys. Everything moves slower when it's cold. Oh, is the computer not working? Plug it in. Oh, okay. It's still not working?
The other side.
What's the monitor? No, it's your computer.
Thanks, Dan.
You need the monitor. Monitor, no, there is a light.
There you go.
And the computer is
Okay.
Are we not going to
This one won't be on the final. Yeah, but I'm still going to teach it to you guys anyways.
Like it won't be on the final as if we don't need to know it, or it won't be on the final as if we do need to know it.
As in you won't need to know it. But for your assignment, you need to know how to use it. It's actually not that bad.
It's just pretty.
No. The thing that scares people is this guy right here. This mu with a little O on it. Mu0, yeah. It's just a constant.
Kilograms per second squared per what's it?
Amp. Because your current, you measure current in amps.
You would think somebody would come up with a clever name.
Like some kind of a unit.
Like an Einstein or something like that. It seems so like it's around names.
Daily, that's guys.
Exactly. It's kind of a dud.
Except the fact that like they learn again.
Well, we don't have to.
We still do. Okay? So your magnetic field, it's based on a few things. It's based on the current in the wire. It's based on the distance that the magnet is from the wire. Okay? Your magnetic field strength and the permeability of free space constant. And this is just, what it does is it just kind of measures, you have that free space there. So this is just a unit of measurement that they use in the calculations. That's constant throughout most electromagnetic, all electromagnetics. magnetism. Okay. There's always a few exceptions to the rule, but don't worry about that. All right. So what is the magnetic field generated? 2.5 meters from a wire carrying 15 milliamps of current. If the current is directed east to west, what is the direction? Or which direction is the field? North of the wire. What? So that's just kind of the big thing I wanted to go about was like directional stuff. Because sometimes this stuff shows up on the departmental. So you know your distance from the wire. 15 milliamps, so that's 3 amps. Okay, so we can find B. So we'll use this big, beautiful new formula. It's just 2 pi r, yeah. $15 times 10 to the negative 3 is just 0.015. That's good, Caleb. Yeah, so I figured out the top 1.89 times 10 to the negative 8 all over now, do you guys remember the unit for measuring electric field?
Yes.
What is it?
My calculator doesn't go that far, so well, I have a calculator, so
It didn't. What? I did it with that calculator and I got this.
mine stopped at the very end.
What? Brennan, you gotta try hard. 1.26 times 10 to the negative 6 times. I got 1.99 times 10 to the 8.
I got 0.0000000000000.
The top right now. Just okay, just. Yeah, I got 1.0004. How did I get the last time though? Well, maybe I did. Or maybe, oh, I used the other one. Just write it like this then. That's fine. But what's the units?
For E?
Yeah. Teslas. Now, the tricky part here is we need to figure out the electric field. So, the current moves from east to west. Here's my wire. It's going to go from east to west, right? Which direction does it go? It goes from positive to negative, right? No, wait, no. Yeah. It always goes from negative.
First thing you showed us, like, negative.
Yeah, it goes negative to positive. That's going to go from east to west. This is positive. This is negative. And if I do, so it's going to go this way, right? No. East to west, sorry, wrong way. I will get there, guys. Just stay with me. No. It should go from positive to negative, right? In a typical battery, it goes from negative to positive.
On the actual direction.
When you put a magnet on it, it goes from positive to negative. That's what I got here, right? Like if you look back at this, positive to negative.
Yeah.
So it's got to go from east to west, so it's going positive to negative. Right?
But it's going from east to west, so I think
West,
west, west, isn't it?
What's that?
Like this, right?
No, it goes from positive to negative.
It's basically just asking us like which way the current wraps around the wire.
Yeah.
Okay.
See, like it goes from positive to negative.
This on the right hand rule.
So based on your hand rule, it's going to go this way, right?
Yes.
So my magnetic field goes this way. You can even just draw like this. Okay? Just on the one side to show that it's going over. That way. Right hand rule. All right. What is the current generated in a wire if a magnetic field of 2 Teslas is detected 0.05 meters away from it? What direction is the current if the wire runs from north to south and the field is directed into the page? All right, so let's quickly calculate for I. E is 2 Teslas. My distance from the wire. So if I set it all up in the equation, don't forget that's a 10 to the negative 6. try this one on your own. You should get a current of 5 times 10 to the 5 amps. 5.0 with 2 sig figs. I got 5 times 10 to the 5. So you're going to times 2 by 2 pi 0.05.
I have 5.0.
You got 4. Brendan, you got to the 10 to the 6?
Hold on, I got 10.
No, it's crazy.
Yeah, I
I
got
keep
it.
getting 490.
Yeah, which is 5, which is correct.
Yeah, that's the right answer.
So why don't you just go 4 point?
Because it's 2 signals.
Yeah.
And if you multiply, and if you like round up that one.
Now I
You
gotta
can't put
sit
4
down
x 4 and 10.
Ooh, that's not right at all, Brendan. I'll tell you that.
Okay, wait, what did I type in?
So, like, if you go, you bring the denominator up to the other side and work it all out. So 2 times 2 times pi times point.
Which, and the bottom comes out to something like, it basically just like, yeah, I got a point, like 0.314 or something like that, and then you multiply by 2, so it's double pi. Well,
I got 498.
I went 6. Oh, I know what I did wrong.
Okay, that's the right answer. 498,000.
Yeah, they divided 2 by the number the first step.
There you go.
Well, I changed the exponent, I gave you a completed answer. That's ridiculous. Actually, I made it small.
Yeah.
No, I understand that. It was supposed to move it by like 1 decimal place, but instead it changed my
All right. Giving Cole a minute. For everyone watching at home, Cole is now punching furiously into his calculator, wondering where he went wrong.
Oh no, I know where I went wrong. The problem is,
All right. Eve, did you get the answer? Eve also did not get the answer. People at home. Did you go 2 times pi times 0.05? You get this as your answer here. Then you divide it by 1.26 times 10 to the negative 6. Oh, okay, yeah. Sorry. It's cold and I'm just tired, chilled. Okay, so we know that the wire runs north to south, right? Oh, the wire runs from north to south. We don't know which way the current goes, all right? We know that this is just the wire. We don't know which way the current goes.
why do we care? Okay, so we just know that it's
But we do know
the direction of the magnetic field,
and the field goes into the page, right?
which would make the current go south.
Yeah, because it goes from
Wait,
east.
wait, wait. Here's a question. Since you're wrapping your hand around it, at some point, technically speaking, it's always going to the page. So which way is it?
Oh, yeah, sorry. Okay, so what direction? Okay, the direction, it's directed into the page to the east of the wire. So here's the east of the wire, right? So that means it's going,
So that means, yeah. That
it's
means
going like this.
It goes around like that, which would mean that its current is going.
Right? So that means your hand, point your thumb up. So the current is going to the north. So if the current's traveling north, That means this has to be the negative end, and this has to be the positive end. I do know they like to ask that about what happens to the poles of a wire and a magnet when you run a current through it. Okay. Okay. Any questions about? Okay. Just the formula itself and how to use it. Are we all okay with that?
I actually have a question. Probably in this one, when it ramps north to south, it's negative, and then positive, but it first it ramps to the west, it's positive. On the first one, it says the current is directed east to west.
Yeah.
Why?
That's the current, the electric current, not the. Quit trying to like throw me off here. I see what you're doing, Brennan, and I don't like it.
Well, I mean, I hope he's like if you didn't see what he's doing, that would mean that he's like actually, which would kind of be very completely different way.
I know it's confusing electric and magnetic fields.
Like, what is the rest of this?
Okay, so the rest of this now. Force on a current carrying wire. If a wire is in a magnetic field, it will experience a magnetic force that acts on it, okay?
Probably one that like it's forced wire and then the next place that formula, but it's substituting in the other one.
Right.
This next formula is what photomath was telling me to do last time.
Good. Hooray for photomath.
Told me I didn't actually need that one.
Now we need to pull.
Okay. All right, this happens since electric charges are moving in the wire and in the magnetic field. So since you're moving something with a force, yeah, you can calculate it. So magnetic force can be measured with current, length of the wire, and the magnetic field strength, okay? So current, once again, is in amps. Length is in meters, and B is in Teslas.
And force.
Yes. Okay, we won't spend a lot of time on this because it's, once again, one of those things that's not really in the final. But I just wanted to tie everything in together. How'd it go, Sam? Okay. To determine the current in a 2.5 meter long wire in a 3.75 Tesla magnetic field if it experiences a force of 25 newtons. If the field is directed into the page and the wire runs north to south, which direction is the force? Okay. We won't spend any time on the direction of the force. I'll just quickly gloss over that, just because you won't have to do that on the final. And we're running out of time, and no one's here, and it'll just be too confusing to teach on a video. Is that okay? Okay. All right, so we know magnetic force, LB. So we would set up our equation. Oh, sorry. 25 newtons equals I 2.5 2.5 times 3.7 9.375 I. Negative I both sides, so 9.375. I equals 2.7 amps. Okay. So a great application of electromagnetic fields. One, there's electromagnetics or electromagnets. You ever go to like a scrapyard and see those big magnets that pick up like cars and stuff? What, you guys don't hang out at the scrapyard? What?
I don't know what you're talking.
You spend too much time on Snapchat. So does scrapyard. Yeah, but but you've seen the things on movies that pick up cars. Those are electromagnets. They run electric current through them. That's how they can turn them on and off, or pick up a car or drop the car. Okay, it's just with electromagnetism.
So if we want to turn on a car, which looks electromagnetic.
If you want to pick one up, sure.
But don't watch more.
Turn one on.
Yeah.
Heat and heat.
No, but I don't have it.
I don't know how to hotwire a car. I'm not going to tell you how to break a car. Steal your own car, like an adult. Another great one is if you take a wire and wrap it up real nice and tight, you can create a magnetic field in the center of it. And if you run electricity through it, you can actually pick things up with that as well. These are solenoids. Solenoids are in our vehicles. We use them all over the place. They're really useful. I was going to bring a solenoid today, but it's somewhere in my garage. And my garage isn't heated, so it's cold. But I can bring one probably tomorrow. It runs on 24 volts. You just hook wire of electricity up, and it.
As you go for runs on this one.
I went for a run yesterday on a treadmill.
Somewhere near Balloon Lake.
What's that?
Somewhere near Balloon Lake.
Yes. I went to the university and ran. They have treadmills there. But I will go for a run outside tonight. It's supposed to actually warm up.
It's supposed to be warmer tomorrow. I would wait. Or warming up, it means like minus.
It's going to be minus 23 tonight by 7 o'clock. So that's my
They're
plan.
gonna go for a run. If you get out of the water, minus.
Yeah.
When the sun is down and it's dark outside.
I wear a headlamp.
That's not the point. My point is the sun provides heat.
Yeah, but as long as it's not windy, it's not. You generate your own heat. You wear enough layers. You're
I'm
fine.
more afraid of getting mugged.
No.
At negative 27, or is
The criminals aren't out in the wintertime.
They will be.
No.
They just say criminals aren't out in the later time.
Not in the wintertime. Not in the wintertime.
Winter time.
It's too cold. Yeah, people got to stay warm.
Like, though they are out, none of the police are out. Like, rob banks.
Right. You see a real spike in bank robberies in the winter. All the bank robbers with their masks on and guns and striped shirts.
Then they'll look like everyone else with their students.
Yeah, see, it's not a bad idea. Brennan, if only you knew how to steal a car, you could be a bank robber. Other applications of electromagnetism, MRIs, we talked about those in health science. You can create magnetic fields with electricity, and
you can throw chairs into them and then like crush them.
yes, and you can generate images of people's internal organs. TV screens work on this now as well, LED, and yeah, I think LED. What's the other?
The E and LED stand for electromagnetic. Oh, well.
No. What does LED stand for again? I have to look it up. Electric guitars, the pickups in them, those have magnetic fields in those.
Light emitting diode.
Oh, I know.
Thank you.
There is a diode.
Don't worry about that. I used to kind of go into that when we used to learn like electric circuits in physics 30. We don't.
Last time we actually learned about
Yeah, you learn a little bit about it in grade 9 and you never touch it again.
Yeah.
We used to do like really complicated circuit diagrams and figure out the amperage and the voltage everywhere. I really liked teaching it.
I'm glad we have a circuit diagram.
That's good. Another one like electric bells and stuff nowadays in like churches and stuff, big bells to make those hammers ding. They use electromagnets and stuff like that as well. Yeah.
Those have like
Yeah. Yeah.
Work for it.
Yeah. No, the old churches all do have those. There's ones in Saskatoon that still do.
There's only one switch button on that school like
No, it's more.
Yes. It's like Quasimodo. I got to do that at my cousin's wedding one time. It was fun. Other bells, even like fire alarm bells and stuff do it too. to make that, they run electric current through there.
I wonder if fire alarms you should have bang on the bell.
And they did.
I mean, in
How do you
like
manage
1920, they did.
Mhm.
Or you normally
And then guys would show up with pails and pretty much like throw water and watch your house burn down. That was kind of what they did.
And they got,
well, it's a lot of like sure.
So advances in electromagnetism. By the late 1800s, James Clerk Maxwell came along and he demonstrated that electric and magnetic fields are actually two different parts of the same thing, so they are interconnected. He came up with all this stuff. His equations are still really famous, but they kind of got eclipsed because they're very complicated. And they're similar to Einstein's theory of E equals mc squared. We're going to get there. We still have time.
You're not gonna have time.
Oh, we totally are. Albert Einstein was able to kind of simplify it, although he still uses Maxwell's theories as well. Okay? Just to give you an idea. Yeah. All right. Any questions about any of that? Okay. So that's kind of it for electromagnetism. Oh, electromagnetic waves. This is what he got into when he tied it in, which makes up electromagnetic radiation, just another term for light. All right, this includes everything from radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. So that whole electromagnetic spectrum is all connected.
what do you look like?
That's where I got this image. Yeah, that's where it's. Okay. So this is the entire electromagnetic spectrum. This is all light particles and waves, which you guys would have learned about in Physical Science 20. I showed you guys this image, I think, like on day 1, day 2. Okay.
What kind of light waves? All the other invisible waves have different colors and
They can be, well, not colors, but they can be detected and seen and interpreted. This is how we do most of our research in space. We'll use like X-rays and UV rays.
Why not Y rays?
What's that?
Why not Y rays?
Gamma rays? They use a little bit of that too. Y rays.
Y rays is more fun to say.
Alright, fair enough. And microwaves, this is how we see most of the things in space. They take that data and they compile it, and they add colors to it, and then you can see things. Okay, so that's all I got.
Okay.
Hopefully the formula and the right-hand rule makes sense. You guys have that worksheet to work on?
I don't.
Or you didn't get? Oh, you emailed everyone.
I told you no.
You did. Okay. There, we have it on video. Brendan was right. I was wrong.